In a groundbreaking study, physicists claim that wormholes may have already been detected. Not only that, but we have also imaged them. Wormholes are hypothetical objects in the universe that connect two distant regions of space-time. They may even connect 2 points in 2 different universes. Physicists have made significant progress in understanding the nature of these exotic structures in the past few decades. Recently, a team of researchers used Google's quantum computer to show that wormholes of general relativity and entanglement of quantum mechanics are essentially the same. And now, a team of scientists has claimed that these hypothetical space-time structures may have already been detected. In fact, the 2 supermassive black holes we imaged so far could be wormholes in disguise. But how is that even possible? If black holes are indeed wormholes in disguise, how can we differentiate between the 2? Finally, and most importantly, why is the understanding of wormholes essential to develop the theory of everything? To answer these questions, it's important to go back 100 years in time. Wormholes were first theorized by Ludwig Flamm in 1916 while reviewing the solutions to Einstein's field equations given by Karl Schwarzschild. Later in 1935, Albert Einstein and Nathan Rosen used the theory of general relativity to expand on this idea. They proposed the possibility of bridges through space-time that could connect 2 distinct points in the universe, no matter the distance between them. They were named Einstein-Rosen or ER bridges. But Einstein wasn't happy about these hypothetical bridges because the equations showed they were non-traversable. So he thought, what's the use of such shortcuts in space-time if no one can use them? In the same year, Einstein and Rosen wrote a paper with another physicist, Boris Podolsky. The Einstein-Rosen-Podolsky, or EPR paper, was on quantum entanglement, which Einstein referred to as a spooky action at a distance. At that time, there was no reason to believe that these 2 papers were linked. In other words, no one could have even thought that ER equals EPR. About 20 years ago, quantum gravity researcher Juan Maldacena mathematically showed that a pair of black holes in a particular type of space is connected by a wormhole. And then in 2013, he realized that wormholes are an outcome of quantum entanglement. That is, ER is equal to EPR. So if 2 black holes are connected via wormholes, they are quantum entangled and vice versa. It is equivalent to saying quantum theory and gravity are interconnected. This duality is a general idea behind the holographic principle, which mathematically relates gravitational aspects to quantum physics. And that is a picture of quantum gravity and the role of wormholes in it. But the most critical question is, how do we discover these wormholes? Unfortunately, the detection of wormholes becomes a problem because wormholes are hypothesized to look like black holes. Therefore, it is hard to distinguish between wormholes and black holes. Nevertheless, a team of scientists from Sofia University of Bulgaria suggest a method to find the difference between black holes and wormholes. They studied certain parameters that may be unique for each of them. So far, scientists have only looked at the similarities between the 2 exotic objects, but this team found out how they differ from each other. First, they studied the polarization properties of radiation emitted by the accretion disk around black holes. Then they compared this with the suspected regions of space where wormholes might exist, and analyzed the polarization properties. The comparison led to the creation of a simplified model of the wormhole's throat. This model could tell how matter encircling the entrance of a wormhole behaves differently from that falling into a black hole. It shows the particles encircling the wormhole's opening are polarized by the strong magnetic field of the wormholes. The interesting thing is that these kinds of polarized emissions were detected recently during the capturing of the first images of black holes at the heart of M87 galaxy and the Milky Way. So if the model proposed by the team is accurate, there's a high possibility that M87 star is itself a wormhole. This leads us to a bigger picture, hinting that wormholes could be hidden in many black holes. But the model only focuses on one parameter, the polarization property of light. To get more grip on the differences between a black hole and a wormhole, an indirect method of observation involving gravitational lensing was also studied. Gravitational lensing is the distortion of a background object's light when it passes near a massive object, such as a black hole or a galaxy cluster in the foreground. The massive object acts like a lens that magnifies the background object. According to the team, the distorted image of strongly lensed objects could indicate significant differences. For example, they found that the polarization intensity of suspected wormholes would be greater, up to an order of magnitude, than a black hole. Also, suppose a suspected wormhole region was detected at an angle where the light is observed passing its entrance. In that case, the radiation from the region across the wormhole throat leads to the formation of an additional structure of ring images, which would further help to understand the polarization properties better. Although distinguishing wormholes from black holes is still tricky, the work of these scientists is a step ahead in the identification of wormholes, which may lead to further discoveries of these exotic objects in the universe. Also, the results from the Caltech team that used Google's quantum computer to create a mathematical version of a wormhole have provided deep insights into the true nature of these objects. They created a circuit that teleported quantum information using quantum bits or qubits, believed to be analogous to a wormhole between two black holes. It's a clear connection between gravity and quantum mechanics. So the Caltech experiment is strong evidence in favor of the holographic principle. And this is a big step toward the unified theory of quantum gravity, something physicists have been developing for nearly a century.